And and that should be okay. Fun times. Yes, he's my little travel buddy. Okay, let's try that. Okay. There we go. All right.
Bom dia, pessoal. Então a gente vai começar agora o último keynote do nosso evento, infelizmente. Mas apresentando para vocês o Russell Keith-Magee. Ele, Dr. Russell, é um veterano de 10 anos do core team do Django, sendo que foi por 5 anos presidente da Django Software Foundation. Ele também é o fundador do projeto Beware, com foco em criação de ferramentas GUI para apoiar o desenvolvimento de software Python. Trabalha como desenvolvedor de software freelance e está profundamente envolvido em explorar formas de financiar o desenvolvimento e manutenção das ferramentas de código aberto que usamos todos os dias. Uma salva de palmas, por favor.
Obrigado, Letícia. E bom dia. Meu nome é Russell Keith-Magee. Essa é minha primeira Python Brasil. E com sua permissão, eu vou dar o resto deste discurso em inglês. I'd like to echo Naomi's comments from yesterday about language. I'm Australian. Australians are amongst the least multilingual people on the planet. I speak barely passable German, restaurant French. You've just heard all my Portuguese. I am in awe of the people in this room that are operating at a technical language in 2 or more languages. So please, come talk to me. Don't be afraid that your English isn't good enough. And if you do, please don't apologise for the fact that your English, which is your second language, is bad, because my Portuguese is much, much worse. Lastly, I'd like to give a huge shout out to the man in the booth back there, who's waving, yes. I have a huge respect for what you're doing. I apologise in advance for how fast I talk. But I also know you have to repeat everything or translate everything that I say. So, right behind that jar, there is a rare spider. The spider scratches the jar as much as the jar scratches the spider. The spider scratches the frog. The frog scratches the spider. Neither spider scratches the frog. Neither frog scratches the spider. Anyone with headsets, how do you do? So, for those of you who haven't met me before, when I'm not taunting translators and transcribers, I've been a member of the Django core team for almost 11 years, and I was president of the Django Software Foundation from 2010 to the end of 2015. Django is a big part of the broader Python ecosystem, but it's by no means the only part. There are other web frameworks. There are great tools for data analysis. There are projects for using Python in education and on embedded devices. None of this happened overnight. Python as a language is 25 years old. It took maybe 10 years for Python to gain significant traction in our industry, and another 10 before it gained really widespread support. What we see today as the Python community is the result of thousands of hours of largely volunteered effort. And despite all this effort, Python has really only been available on server and desktop environments, devices that fit a very traditional concept of what a computer is. But over the last 10 years, we've seen the emergence of a whole new class of computing devices, much smaller and often portable. Things like phones and tablets and watches and set-top boxes. My reading of the tea leaves is what has led me to change the focus of my open source contributions over the last couple of years. These days, I'm spending most of my time not on Django, but on the Beware project. Now, for those who haven't come across it before, Beware is an open source collection of tools and libraries for creating native user interfaces in Python for desktop, but also for iOS, Android, single page web apps, and any other new hardware platform that comes along. In other words, I want to Python all the things. I really like Python. I think it's an elegant, expressive, most importantly, readable programming language. It's got a great system library and an even richer ecosystem of tools around the outside of it. I love the minimalist syntax and significant white space. To me, that's just enforcing at a language level code style guidelines that are good engineering practice. I'm not going to claim that Python is perfect, but it's as close to perfect as I've ever come, and I'm very happy living my life as a Pythonista. And because of that, I want to be able to run Python on my devices, not just some token notion of running Python. I want to be able to use Python to deliver a full developer experience. I want to be able to develop and deliver applications for these platforms, not in some Python sandbox or on jailbroken devices, but as a fully fledged, first-class citizen of their device ecosystems. Now, if you're here today, I probably don't have to convince you of the benefits of Python as a programming language. What I might need to convince you of is that this is plausible or even desirable to run Python on non-traditional devices, and assuming that it is possible, that it's worth the effort to try. So that's what I'm going to talk about today, the how and the why of Pythoning all the things. Okay, so first off, let's deal with the how. There's no point in getting all philosophical about why you should do something if you can't actually do it. So let's play a game. You have some fancy new hardware device dropped into your lap. What options do you have for getting Python running on that device? Well, to answer that question, we need to start a little bit higher up with a slightly different question. We need to start with the what. What is Python? Well, it's a programming language, right? Except that it isn't. Depending upon who you're talking to, Python could be one of two things. Python, the language, is an abstract thing. It's a specification of syntax and semantics that describes how a particular sequence of human-readable bytes will be interpreted to make a computer do something interesting. Then there's the Python interpreter that you install and run. When you tell someone, go to the Python website and download the installer, you're not strictly talking about Python, you're probably talking about CPython, which is the de facto reference implementation of the Python language standard. This separation between implementation and specification is valuable because it means that CPython isn't the only way that Python code can be interpreted. There are features of Python that are experienced by end users that are features or misfeatures of CPython, not the language itself. For example, the GIL, the Global Interpreter Lock, which is the bane of any discussion about Python performance, is not an inherent feature of Python, the language. It's a feature of CPython, a specific reference implementation of the Python language specification. CPython, because of the way it's implemented, has a GIL. Other implementations of the Python language specification, Jython, PyPy, Stackless, they don't have a GIL. So this separation means that when we're talking about getting Python running on our fancy new hardware device, there's a couple of different approaches depending upon the capabilities of the device that you're targeting. Now, the easiest, obviously, is to just use CPython. When you start a Python shell or you run a Python script on your laptop or on your server, chances are this is what you're doing. You're running CPython, effectively the reference implementation of the Python language standard written in C. And one of the side effects of being written in C is that it's really easy to port to new platforms. In this regard, it follows the tradition that was laid down by Unix. One of the major reasons for the success of Unix as an operating system is that during the early days of computing, dozens of manufacturers were producing computers. IBM, DEC, Univac, NCR, Honeywell, General Electric, Siemens, Fujitsu, Hitachi, NEC. And technology was advancing so quickly that there would be major shifts in architectures between versions of a device. And each device would come with its own eclectic operating system. Then Ken Thompson, Dennis Ritchie, Brian Kernighan, and a bunch of other people working at Bell Labs worked something out, that if you could define a minimal kernel that could be ported to any machine, providing a common API for operations like memory management and process invocation and input-output, then you could use that kernel to bootstrap the rest of an operating system. And then they developed a programming language, C, to make that even easier. The original versions of C were developed to make it easy to port Unix to other platforms. The kernel, which was written in assembly language for a specific machine and architecture, got smaller and smaller, and the operating parts of the operating system could be easily ported to this new kernel whenever it got ported over. And that's essentially what CPython looks like when you want to port it, just at a slightly higher level of abstraction. CPython assumes the existence of a C compiler, but as long as you've got a C compiler, which is a pretty safe assumption on most platforms these days, the CPython core can be compiled, giving you a Python interpreter that you can then run and embed the same way that Python can be embedded on a normal desktop platform. And the existence of a C compiler, that's a threshold that most modern devices can support. If you look in the lib directory of the Python 2.7 source tree, this is what you'll find: a list of all the platforms that have explicit support in the Python source tree. Now, in Python 3, a few of these got pruned out. So OS2 EMX, for example, has been dropped. Any old OS2 users in the room? No? We managed to avoid that one? Okay. What about BIOS 5? Any BBox users? No? Okay, I got a couple of flags last time I did this. So yeah, so they're both gone now. They've been pruned out because nobody's really using those platforms anymore. But hopefully the point is clear. As long as you can compile the kernel, the core C Python implementation, you can get the rest of the Python standard library and the whole Python ecosystem for free. But even this compilation process gives you some options. If you're using a compiled language like C, the usual approach is to write some code and then use the compiler on the same machine that you intend to run that code. If you're on a desktop or a server machine, that makes perfect sense because you almost certainly have a C compiler. After all, you had to have one to port Unix there in the first place. But on some devices, this isn't plausible, either because a compiler hasn't been ported to that platform or because compilation on the device isn't actually plausible. Consider, do you really want to be running a compiler on your watch? Compilation is a CPU-intensive process. Do you really want your watch turning into a molten ball of slag and burning a hole to the center of the Earth while it's attached to your wrist? No. So you have to have a way to compile somewhere else and then get that compiled product onto your watch. And that's what cross-compilation is. A compiler, at the end of the day, is a magic box that takes human-readable input and produces machine-readable output. But there's nothing that says that the machine-readable output has to be read by the same machine that is doing the compilation. It's just bytes at the end of the day. And yeah, okay, it's a little bit more difficult to set up and there's plenty of opportunities for things to go wrong, but they are all resolvable problems. And Python has this ability to cross-compile built into its build system. This is something you almost get for free when you use the GNU autoconf toolchain like Python does. I say almost because GNU autoconf is a very special snowflake. But at least in principle, the GNU toolchain has been designed to support platform cross-compilation. Remember, this is the reason why C compilers exist, to make it easy to port a binary to a new machine. Okay, so as long as you have a C compiler that runs on your new hardware device and you have a C compiler that can target that device, you're set. You can compile the stock CPython sources and get the same CPython that you use on a server. Now, this doesn't necessarily mean that you have the same Python experience, though. If you're running on a watch, you can't just open a shell prompt and start typing in commands. So you have a problem. How do you interact with Python when you haven't got standard in and standard output? Are you stuck? Well, the good news is no, you're not. CPython is written in C, and while it's certainly designed to be invoked from the command line and provide a prompt, it doesn't require that. The command line experience that you have with Python is essentially just a wrapper around a very specific collection of setup and teardown tooling. The code for the Python executable is itself remarkably simple. It's really just a pipeline for getting keyboard input and output and pushing it into the Python interpreter, called, not surprisingly, libpython. This library is what implements the actual run this Python code part of the puzzle. So as long as you can build a binary, any binary, that initializes some key methods in libpython, you can have Python running on the device any way you want, and then it's up to the device to determine how to push the Python script into the Python interpreter running on the device. Once you've got a running interpreter, you're going to want to access the system native libraries so that you can actually interact with the capabilities of this new device you've got. Now, you've got this far, so that's because you've got a C compiler, which means you've generally got a C library under the hood providing those services. And this means you can use one of the features of the Python standard library, ctypes, to access those services. Ctypes is a library that exploits the fact that at the assembly language level, the way that you invoke a function, what's known as the calling convention, is the calling convention used by C compilers is well defined. And because it's well defined, you don't have to use a C compiler to generate code that will be interpreted as a C function call. Any tool that can generate a compatible sequence of assembly language commands can invoke any function in the library, regardless of what language is doing the calling or what language the library was originally written in. And there's a helper library called FFI, the Foreign Function Interface, that makes this easy to do, and C-types is Python's built-in wrapper around libFFI. Using C-types, all you have to do is reference a C library, then describe the prototype of the C method that you believe to be there, and then you can invoke it directly from Python without the need to compile anything. So, for example, we could use C-types to load libc, the standard C library on a POSIX box, and we can tell that library that the function stircher takes a character pointer, and it takes a C character, and it returns a C character pointer, and then you can invoke that method. Now, there's no compilation here. This is pure Python that accesses the underlying C library directly. So whatever system libraries your platform provides, you can access them from Python. And if you want, you can then write wrapper libraries around it to provide a nicer API, but that's up to you and the interface you want to provide. And at that point, what you have is a fully functioning Python on your new hardware device with full access to all the system libraries. Now, when this approach works, it's pretty straightforward to get going. It's the approach that makes Python available on pretty much every desktop and server that's in production. It's also the approach that I've used to get Python working on iPhones, iPads, Apple TV set-top boxes, and in principle, Apple Watches, but I've only kind of done that in the test bed. I haven't actually put it on a device yet. Although Apple hides a lot of the details behind Xcode and Objective-C and more recently Swift, the core of what they're doing on those devices is plain old Unix and C. And so compiling CPython for iOS, tvOS, watchOS is relatively simple, and you can access the native system libraries using C-types. But what about when this doesn't work? What happens when you don't have a C compiler, or when C isn't the native system language? Like, for example, on Android. Well, then you have to take a different approach. If you read the advertising copy for Android, it sells itself as a Linux, and then promotes Java as a user-space programming language. The catch is, it's not really either of those things. Yes, it is Linux at some level, but there's not at any level that's interesting to us as end developers. The kernel is written in C, and you can use a C compiler that will target that kernel, but the C layer only has access to bare-level system services. So you can't really do anything interesting from the Android as a personal computing, portable computing platform perspective. All of Android's user space libraries are exposed using Java APIs. Now, Android isn't the only platform that does this. Sun, now Oracle, has spent a lot of money developing the Java ecosystem, which is an entire ecosystem based around using the JVM as a runtime platform, abstracting away hardware differences. Both of these platforms do a head feint towards the significance of native libraries. Android provides NDK, the native development kit. Both Android and JVM provide JNI, the Java native interface. But the focus of this tooling, or the focus of tooling for those platforms, is very heavily directed at using Java for user space code. So, yeah, you can use Python on Android or Python on JVM using CPython as your starting point, but it's not the natural interface to the platform. Your life is going to be a lot easier if you work closer to what the platform wants you to do. There are also platforms where it just isn't practical to use CPython. MicroPython is a good example of this. CPython is a great implementation of Python as a language specification, but embedded devices have very extreme constraints in comparison to servers and laptops, and CPython is just too big to fit in an unmodified state in an embedded microcontroller. So you have to look at other ways of providing an implementation of Python if you want to use it there. So if you've got one of these platforms and you want to use Python on it, you effectively need to provide a new implementation of Python, one that is using the native capabilities of that platform. So how do you do this? Well, there are a couple of ways to tackle that problem. One option is to use a different compiler. CPython is obviously intended to be compiled using a C compiler, but there are C compilers out there that don't target traditional system binary executables. One such compiler is Enscripten. It's a compiler, strictly a compiler backend, because it plugs into the parser that's provided by Clang, but rather than outputting a binary that can be executed, it outputs JavaScript, specifically a subset of JavaScript called ASM.js that's known to run fast on certain JavaScript implementations. Remember, a compiler is just a box for turning human-readable bits into machine-readable bits. Nothing said the machine-readable bits had to be machine language. And if you take this approach, what you get is PyPy.js, a project by another Australian, Ryan Kelly. PyPy.js takes the PyPy source code, so the just-in-time compiled fast Python interpreter, and passes it through Inscripton. And what you get at the end of the day is a block of JavaScript code that will run Python code. And for carefully selected benchmarks, it runs that code faster than CPython on the same machine. Now, if you're not just going to recompile existing sources, though, you'll need to re-implement CPython. But you don't have to re-implement all of CPython. What do I mean by that? Well, if you pull apart a Python implementation, there are a number of pieces. The full stack consists of a parser, which takes human input and turns it into an in-memory representation of that code. There's a compiler that takes the in-memory representation and turns it into something that can be executed in CPython, that's bytecode. There's an eval loop, which reads and runs the output of the compiler, and this is what you experience as the Python executable. And then there's the standard library, which is used by the code to run through the eval loop. The standard library comes in two pieces. There are bits that are written in a native language, and there are bits that are written in Python. The bits written in native language are either system-specific, so for example, hitting a raw system call to spawn a process, or they're done natively for performance reasons. The simplest approach, re-implement the whole thing. Rewrite the lot in Java or C# or whatever other language you want to target. Those parts of the system library that are written in Python don't need to be re-implemented, but the rest you port over. And that's effectively what MicroPython and Jython and IronPython and Sculpt and Brython and a number of others do. Wholesale re-implementations of the whole of the Python language specification, except for the bits of the standard library that are written in Python and therefore can be reused as is. But that's not the only approach you can take. You don't have to throw out the entire CPython stack and start from scratch. CPython provides, not surprisingly, a really good parser for Python code that outputs a data structure that is parsed, ready to manipulate version of the code that has been entered by a human. This data structure is called the AST, or the Abstract Syntax Tree, and it's a representation that has been designed to be manipulated and converted. The normal CPython compiler takes that AST and converts it into bytecode that can be easily compiled by CPython's event loop. However, you could just as easily take that AST and turn it into any other representation that might be useful. For example, Java bytecode or .NET CLR bytecode. And that this is what Voc does. Voc is effectively a cross-compiler for Python code. It's a compiler, it's written in Python, so it can be executed by CPython, but what it outputs is Java bytecode that can be run on any JVM instance. And when that Java bytecode runs, it's indistinguishable from code that came from native Java source code, but it refers to line numbers of Python source code that generated it. Okay, so we can reuse CPython's parser. Do we have to stop there? Is there any more of CPython that we can reuse in our quest to get Python on different platforms? Well, yeah, if you want to, you can reuse CPython's compiler too. When you run some Python code, it's written in a .py file, and you pass it through CPython, it outputs a .pyc file. That pyc file is the compiled form of that code. It's a binary representation, but not a system binary. It's not executable by Python itself. It's a bytecode representation. Bytecode is a bit like high-level assembly code. It's an encoded set of instructions for a stack-based virtual machine, and that has basic primitives like pushing and popping things onto a stack, setting attributes on an object, and so on. There's nothing about Python, the language, that specifies bytecode. It's a runtime format used by the CPython interpreter. The CPython interpreter is what provides the virtual machine that can actually execute that bytecode. There's nothing to say that you can't implement an independent implementation of the CPython virtual machine capable of running CPython bytecode. And this is what Batavia does. Batavia is an implementation of the CPython virtual machine written in JavaScript. And because it's written in JavaScript, it can run in the browser. And while this might seem daunting, it's actually not that hard. After all, CPython bytecode only has 100 or so operations, and a good chunk of those are basic mathematical primitives, add, subtract, multiply, divide. So re-implementing it doesn't actually take that much code. The biggest complication is that CPython, because it's an internal detail, makes no guarantees about compatibility between bytecode versions. So between Python 3.4, 3.5, and 3.6, there have been major changes in bytecode format and interpretation. But you can stay on top of these if you want to. It's just not a major problem. It's just kind of an annoyance. Now, whenever I tell people about Batavia, their first reaction is usually, well, why not just compile Python code into JavaScript code? And, well, yeah, okay, that is an option. On the surface, it even seems like a relatively easy option. Sure, there are some syntactic differences between Python and JavaScript, but a lot of those are cosmetic, right? They're just, braces, different looping constructs, whatever. But if you dig deeper, it actually gets a lot more complex than that. You don't just want a language that looks like Python. You want a language that runs like Python as well. And Python's scoping rules are very different to JavaScript's. Take this example, take this as an example. These two code snippets are cosmetically the same, modulo the language translation. The only thing that's a little bit hairy is the change to the arguments in the print statement. In JavaScript, it uses the concatenation by plus. In Python, we can just add additional arguments. Okay, so what gets output when you run this code? What does the JavaScript console output? It outputs 30. What about Python? It's an unbound local error. Because X, under JavaScript scoping rules, X is in the global scope. Python's scoping rules means X can be accessed for reading, but not for modification. And yeah, okay, sure, if you used ES6 let in the JavaScript version or you use global in the Python version, you'd get output parity and they'd be the same. This is an intentionally simple example to illustrate the point. The problem gets a whole lot more complex when you have structures like closures and more complicated constructs of functions inside functions and so on. So if you want to preserve Python's semantics in JavaScript, you can't just do a syntax transformation. You actually have to parse the code and generate JavaScript constructs that expose the same lexical scoping that Python expects. And that means you're left with basically three choices. You either re-implement Python scoping rules in JavaScript, you treat the resulting compiler as a Python-like language, something that looks like Python but has lots of subtle differences, or something between the two. And it turns out that it's a lot easier to just implement the bytecode machine because all you have to deal with is a simple stack. So what's the downside of using Python's parser and or compiler? Well, it means you've made a decision that parts of your stack won't be running on your new platform. If you're using CPython's parser and compiler, then obviously that part of the stack will only run where CPython can run. You're effectively cross-compiling your Python code, using one platform to produce a binary that will work on another platform. This means your target platform won't have the ability to parse and compile code on its own. So that means the one thing you don't get on the new platform is a REPL, the read, eval, print loop. You won't get a Python prompt where you can interactively type and execute Python code. Having a REPL depends on the ability to compile code. And if you don't have native compilation capability, you can't have a REPL. Now, that might seem like a big omission, but the platforms we're targeting aren't natural matches for a REPL. Nobody really wants to be typing Python code on their watch, remember. So on these devices, Python is really just about being a high productivity programming language, not an interactive one. And you also have to think about the whole development cycle. Remember, one of the reasons we're porting Python is so that the same code can run on multiple devices. So you can develop your code on your desktop machine using CPython and a REPL and some mocking or stub libraries. And then once the core logic of the application works, ship it to the device for some final testing. Okay, so at this point, either by re-implementing or borrowing from CPython, we've got ourselves a parser, a compiler, and an evaluation or an eval loop. So you can run your Python code, but only code. There's still a big piece missing, the standard library. The CPython standard library is made up of two parts. There's a pure Python part and a part that's written in C. The bit that's written in pure Python is easy. You just take that code and use it wholesale. It's Python code, so it compiles like Python code, the same as everything else. We can compile it to bytecode and run it on our new virtual machine. We can cross-compile it to a new target platform or just run it on our re-implemented Python, whatever it is you need. But the bits written in C are a little bit more complicated. First, there are a couple of reasons why a module might be written in C. First, there are occasions where what you're doing is talking directly to system native services. If you're going to make a POSIX exec call, well, you're going to need to call the C method that implements that call. But there are also modules that are implemented as C modules because they're a wrapper around some library whose native implementation is in C. bzip2, for example, is a compression library. The reference implementation is written in C. Sure, you could rewrite it, but why would you? Let's just use the reference implementation. And lastly, there are parts of the standard library that are implemented in C for performance reasons. For example, the decimal module used to be implemented in pure Python, but then for performance reasons in Python 3.5, it was turned into a C module. And that's great for CPython as an implementation. Nobody's going to complain about more performance. But if you're looking at CPython as a reference implementation, it's a bit annoying because all of a sudden you have something that you need to re-implement natively. What we really need here is a reference standard library, an implementation of the Python standard library that's written entirely in pure Python, except for a clearly delineated minimal interface to system services. And that's what Ouroboros is. Now, for those not up on your Greek mythology, Ouroboros is the symbol of a snake eating its own tail. Ouroboros is very much a work in progress, but it's an important part of the whole puzzle if we're going to make it easy to bring Python to as many platforms as possible. The last piece of the puzzle is deployment. Now, this is an area where Python really hasn't had a good story. Even in the web world, which is considered one of Python's strengths, Python's story lags a long way behind other languages like PHP. A PHP developer just needs a directory they can upload their code to, maybe some details about the host address for a database, and they can deploy their site. A Python web developer needs to know about WSGI and web server configuration and mechanisms for activating virtual environments. Now, it's not too daunting once you know what all the pieces are and how they're supposed to fit together, but it's certainly a long way from one-click deployment, and definitely a lot more daunting than most first-time developers are really ready for. And as hard as it is to believe, the situation is worse for desktop code. You want someone with a Windows machine to run your Python script? Good luck with that. You better hope they've got admin access to the machine and that they know how to find the dialog 3 levels deep in the control panel that lets you set the path environment variable, because every Windows user knows how to set the path, right? Yeah? Now, the good news here is that the problem can be solved. And moving to platforms like phones and watches is effectively going to force us to, as a community, to address these problems. These devices don't have a control panel. So if you want to distribute apps for these platforms, you have to package them as standalone tools with a simple entry point. And if we have to develop these tooling for these new platforms, then it makes sense to look at the tooling for existing platforms while we're at it. And this is what I've been trying to do with a project called Briefcase. Briefcase is a distutils extension that will convert a Python project with a setup.py file into a deployable, distributable unit. Now, again, it's early days for Briefcase, but it works for macOS, it works for iOS, tvOS, has some preliminary support for Android. If anyone has interest in Windows, I've got some ideas and I'd definitely like to talk to you about those. But what you get at the end of the day is Python setup.py iOS, and it spits out an Xcode project that you can compile, run, and ship to your phone. Python setup.py macOS, and it gives you a .app file that you can give to someone else, and it just runs. Okay, so a lot of the very specific tools and libraries that I've been talking about so far have been at very early stages of development. The flip side is that this means there's a lot of very fertile ground for contributions. If you want to get involved, I'm here till the end of the sprints. No matter your level of expertise, come and grab me, and I guarantee I can find something for you to work on. And if you do, many thanks to Revolution Systems, I have shiny little Beware contribution coins that you can earn. Okay, so that's the how. That's how you introduce Python to a new hardware platform. But why? Why is this important? Why have I spent so much time and effort trying to get Python to run in places where it doesn't currently run? For me, it's about evaluating our existential threats as a programming community. Python is on a crest of a bit of a wave at the moment. Over the last 25 years, we've built up a community and resources and expertise. And as a result, most surveys put Python in the top 4 or 5 programming languages that you should know, usually only behind Java, C, C++ in some various order. The growth of events like Python Brazil and PyCon in the US and so on is a great indication of that sort of success. So in the midst of that success, it behooves us to look to the future and consider whether the light at the end of the tunnel is the dawning of a bright tomorrow or a train coming straight for us. We need to ask, quo vadimos? Where are we going? Python has been around for 25 years. It was originally found a foothold as a systems integration language on servers. Over time, it found another niche in web servers, resulting in Zope and Django and Pyramid and Plone and others. The era of Python as a major web platform is, at least 10 years old. Since that time, Python has found footholds as an education language, as a data analysis language. It's found these footholds because it's an easy, straightforward language to teach while retaining the power of a hardcore computer science language. And we've developed a reputation, we've developed a community, we've developed a rich ecosystem of tools and libraries around this core language. So what changes are coming that pose an existential threat to all of this? Well, the most obvious one is the thing I've been addressing directly so far. The last 10 years has seen an explosion of platforms that people are using for computing and the types of people that are using these platforms. Computers aren't just for geeks anymore. These devices have rapidly become an indispensable part of everybody's life. And that means these new platforms are becoming an increasingly important part of the development landscape. If Python doesn't have a good story on mobile, we run the risk of being left behind. Servers aren't going to go anywhere, but they've only ever been used by a very small proportion of the overall community. And the growth of services like serverless computing is part of a larger trend to hide even more of those server-side details. As for desktop machines, sales trends of desktop machines versus phones and tablets, they're certainly pointing to a time where desktop machines as we think of them today either won't exist or will only exist in a very radically different form to what we see today. So if using a general purpose language that can only be used in a tiny portion of computing devices, what hope does the language community as a whole have? I'd argue not much. But that threat is also a huge opportunity. Many of the areas where Python has gained traction, in science, in education, these are areas where these new devices have the potential to make a huge impact. Imagine a world where a scientist can knock up a quick user interface to put in the hand of experimenters that he wants to gather information, or provide an app so that citizen scientists can log local flora or fauna or environmental conditions. Imagine a world where you can get kids excited in programming because they can build something that runs on their phone that they can show their friends. Imagine a Django Girls style event where students leave the tutorial having not just built a blog, but built a mobile phone app that they can use to upload photos to that blog. Python is a general purpose language. There's no reason it has to be tied to historical platforms. We just have to pay attention to the new platforms that are emerging. So, what are we competing against, and what advantages does Python bring to that fight? Well, we're competing against a background environment where polylingualism is required. At present, there isn't a single programming language that can be used on every platform as a native offering. Apple pushes Objective-C and Swift as their preferred languages, Android pushes Java, the web requires JavaScript. So today, if you're a scientist or a student and you wanted to write an app that's available on multiple platforms, you have to learn 3, maybe 4 different programming languages. Polylingualism, be it in human languages or computer languages, is a good thing. There are countless studies out there that reinforce the benefits of learning a second spoken language, improvements in perception, in memory, in decision-making, problem-solving. The same is also true of programming languages. Learning a second or third or fourth programming language, especially when it uses a completely different programming paradigm, is a great way to encourage your brain to think about problems in different and creative ways. And if you're a professional computer scientist or software engineer, I'd absolutely encourage you to learn as many programming languages as you can. But that's not the market we're talking about here. Unlike spoken languages, there isn't an obvious first contact language. If you were born in Florianopolis, your first spoken language will almost certainly be Portuguese. If you're born in Perth, it's almost certainly going to be English. But in computer languages, there isn't an obvious first contact programming language. There isn't a programming language that everyone in a community speaks. And that means there's ground to be won. It's this first contact status that, to my mind, is critical. Consider the world 20 years ago. Visual Basic was one of the most widespread programming languages in common usage, not because it was especially powerful or useful, especially powerful programming language, but because it was present on every Windows computer, was accessible to non-expert users, and enabled people to do really powerful things with the Office suite of apps. Visual Basic was their first contact language, and many users never moved beyond it. There is immense power in being the language that people use to discover programming. And Python has repeatedly demonstrated that it's a great candidate to be the first contact programming language. From Django Girls to university-level computer science courses, Python has been used as an introductory programming language. And yet, it's also a programming language that is able to support very sophisticated computer science concepts, like generators and asynchronous programming and so on. When marketing people talk about selling a product, they often talk about conversion funnels. A conversion funnel is the idea that there is an entire world of people out there, but they have to move through your sales process before they buy your product. At each step in that process, some loss is inevitable and the funnel narrows, but the goal is to minimize the amount of loss between each step and end up at the end of the day with viable output coming out of the funnel down the bottom. It helps to think about the adoption of software projects in similar terms. There's an entire world of potential users out there. Some of those people will try your product and become new users. Some of them will become regular users. Some of them will become community members. Some of them will become contributors. Some of them will join your core team. Some of them will become community leaders. Now, there are two ways to hack a conversion funnel. You can work on the funnel itself and minimize losses as people move down the funnel, or you can put more people into the funnel to start with. Ideally, you do both. And that's the real opportunity on the table here. We have a world of people out there who look at their computers, their phones, their tablets, their watches, their set-top boxes as devices that they use to passively consume content through apps that are developed by someone else, usually some sweaty geek sitting in a basement. We have an opportunity to break that mold. Not just to make it easier for experts to develop apps, but to introduce a whole new audience to the idea that computing devices can be transformed to do what they want them to do, to meet their needs. There will always be a place for experts, but this new audience isn't looking to do a 3-year degree in software engineering before they get started. They want to learn one language and have that language be useful wherever they go. But if we're putting more people in at the top of Python's conversion funnel, we're also going to get more people filtering down to the bottom, and that means more experts. And if we play our cards right, it's a more diverse range of experts, not just sweaty geeks sitting in basements. People from a wide range of social, racial, economic backgrounds with rich and diverse experiences to bring to the discussion to shape the evolution of the world around us. So, why do I think Python has a compelling case to be this first contact language? Well, it would be very easy for me at this point to launch into a blistering technical critique of JavaScript or Swift or Java and a defense of Python's technical superiority. But I'm not going to do that. Firstly, because I don't think it adds anything to the discussion. Like it or not, JavaScript, Swift, Java, these languages exist, they're in widespread use, and their implementations are battle-tested. No amount of me standing here wailing about WATs is going to make JavaScript go away. It's here, and it's going to stay. And it's pointless to make the argument. History has repeatedly shown us that technical superiority of a technology is very rarely enough to guarantee victory. Betamax and VHS, Windows and OS2, AC and DC electricity. As long as there are at least two options that meet basic operational requirements, the social structures and power relationships around a technology are so much more important than the technology itself for assuring success. The good news here is that Python has a compelling story when it comes to these network effects. Firstly, there's a huge breadth of domain knowledge that's encoded in Python through projects like NumPy, SciPy, Jupyter, BioPython, AstroPy. There is a wealth of scientific experience in our community. Raspberry Pi, Grok Learning are leaders in the world of education. There isn't just a web community or a browser community. We are a true multidisciplinary community. And it'll take a long time for other languages to develop analogous tooling. The Python community also has very strong social credentials. The Python community has been an industry leader in improving participation of women, people of colour, different ethnic backgrounds in our tech communities. Python and Django were amongst the first programming communities to adopt codes of conduct as standard operating procedure. Initiatives like PyLadies and Django Girls have made amazing contributions to the participation of women in our industry. In web design circles, it took a long time to convince people that accessibility is something worth paying attention to. But it turns out that if you focus on accessibility, you don't just make it easier for the deaf or the blind or the neuroatypical to access your website. It improves the experience for everyone else as well. There's a direct analogue with the social leadership position that Python as a community has taken. Yes, we have adopted codes of conduct because they are a clear signal to women and minorities that we want our community to be welcoming and inclusive and friendly. But as a side effect, it makes the community nicer for everyone. A code of conduct isn't there so that women can publish men who are all evil. It's there to make sure that everyone, including the men, have a pleasant experience in a welcoming, friendly community. But before I give myself a sprain from patting myself on the back or the Python community on the back quite so hard, don't get me wrong, there's still a long way to go. But if you compare where we are today to where we were 10 or 15 years ago, we've made some huge strides. I'd like to draw attention to two closely related areas that I think we need to pay more attention to. The first is the spectre of burnout in our community. Now, I started this talk discussing the fact that the bulk of the work on Python and Django were the result of volunteer efforts. About 18 months ago, I hit rock bottom in what was ultimately diagnosed as a major depressive episode. There were a number of underlying causes for that episode, but one of them was the pressures imposed by the volunteer work that I was doing in the Django community. Now, I'm a lot better now than I was, but I've still got a long way to go. But I'm not an unusual case. I've lost count of the number of talented developers around me who have burnt out or come very close under the load that's been imposed by volunteer efforts they're doing in an open source community. And in some incredibly tragic cases, people have taken their own lives over this. This isn't a problem with an easy solution. It isn't as simple as just telling people they don't have to volunteer anymore. Because if you're the maintainer of an even moderately successful project, I guarantee their inbox is filled with "why haven't you fixed my bug yet" emails, sometimes from people who should know a lot better. The greatest shocks in society occur when something that we assume is plentiful and ubiquitous disappears. Petrol, electricity, clean water. If your open source project isn't planning for the day when your biggest contributor steps down or is unable to continue, then your project has a clock on it. And as a community, we need to institutionalize the minimization of the expectation of free labor. If you've got a project role that is going to take resources, be it material, labor, emotional energy, don't just assume those resources will be available forever in boundless quantities. And if you're a free consumer of those resources, be aware of what it is that you are consuming. If you're a commercial organization who depends on a project and you aren't taking steps to contribute to the projects that you use, then I'd argue you're being criminally negligent to your customers and your investors because you haven't secured your supply chain. You haven't mitigated a key risk associated with your technology stack. But it's not just about finger pointing at bad projects or bad users or bad companies. As a community, we also haven't established the conditions where companies are readily able to mitigate these risks. The free software community has spent a lot of time and effort discussing and defending the importance of user freedoms. However, they've been almost silent on the unintended consequences of that position. That when software is free as in freedom, it's almost certainly free as in beer as well, which means that the task of making an income off that software is much harder. Now, I don't want to undersell the importance of user freedoms, but to focus on user freedom to the detriment of the mental and physical health of the developers of that software is, in my opinion, incredibly negligent. How to make money from free software is a question that doesn't have a lot of good answers at the moment. As a community, we need to have a very serious discussion about the economic consequences of our decisions and how to harness the not insignificant resources of a software community has at its disposal. The good news is that there is an unexpected benefit to facing these problems head on. Finding a way to pay for the resources we're consuming certainly helps to stave off burnout, but it has the added benefit that it broadens the list of people who can do the work. Volunteers, by definition, are made up of people who have the time to volunteer. If you've got a family, if you've got children, or a loved one who needs care, those commitments take priority. Well, they should. You want to, and therefore it limits your ability to volunteer. You want to address diversity? Make sure you're not just drawing from the pool of people who have free time, which, broadly speaking, means white, middle to upper class men aged 16 to 30. If you're someone who uses open source, don't just take. Give back in tangible ways, either with hard commitments of time or with cash that organisations like the PSF or the DSF can use. This is especially important if you're a large organisation that has extraordinary resources at your disposal and who derive immense benefit from open source and volunteer projects. Now, you notice that in this talk, I've spent almost as much time talking about the soft, for want of a much better word, aspects of the problem we face, or the problems we face, as the hard technical problems. The technical aspects of computing almost always gets more attention, but they're also the easiest ones to solve. They either have an answer or they don't. Open source projects are ultimately about communities of people with aligned interests, acting collectively. This means issues of communication, collaboration, identity, social justice, inclusivity, funding. These are all intertwined with technical aspects, because without the soft aspects, the technical aspects can't be solved. And these challenges don't have simple answers. Who would have thought humans are difficult? And this is something that's taken a very long time for the tech community to learn. We've still got plenty that we have to learn. The key is to pay attention to it. Whatever software community or communities you're part of, keep your ears open, your mouth shut, and look for ways to improve those social aspects around your project. And part of that means acknowledging any kind of privilege you may have. And when I say that, I don't just mean white men either. Naomi spoke about yesterday, women can have privilege too. So can people of colour. If you don't believe me, go hunt down Saron Yabarek's keynote from DjangoCon US earlier this year. She gives a fantastic explanation of what privilege is and how she, as a black woman, has all sorts of privilege. So what does the future hold for Python? Well, I don't know. I've outlined what I think to be the threats and opportunities, but I'm just one voice. But if we want Python to continue to be a force in the world of computing, I know we can't stand still. We need to prepare for the future, whatever we perceive that future to be. For myself, I'm intending to keep working on Beware, the umbrella project that covers VOC, Batavia, Ouroboros, Briefcase, many other tools that are used to get Python code in the hands of end users, and to enable those users to get involved in writing their own apps. And if any of those projects sound interesting, again, if you want to get involved, we appreciate any help. There's plenty to do. We've got an open offer to mentor anybody who wants to get involved from any level of experience, and even if it's your first time contributing to an open source project, especially if it's your first time contributing to an open source project. And as an added bonus, again, thanks to Revolution Systems, anyone who does contribute gets the shiny. Without funding, though, this is going to continue to be a hobby project. I'd like to see it become a whole lot more. I'd like to see it become a model of a new style of financially viable, socially responsible open source organisation. I'm exploring options to make that happen. One of the options is crowdfunding. If you'd like to be notified when those plans evolve, I encourage you to visit that URL, click on the link, sign up for announcements. Or if you're already sold, you can actually become a financial member of the project already. There's a couple of different membership options there. If you want more details, go to the website or come and talk to me. All this really comes down to is the old quote from Blaise Pascal. If you want any project to be, fortune favours the prepared mind. If you want any project to be successful or remain successful, you need to plan for that success. It took years for Python to become an overnight success. Django certainly benefited from some early momentum from being in the right place at the right time, but real success, true success, took several years. I've benefited from being part of large and successful projects like Django. I'm in the early stages of what I hope will be equal success with Beware. But a lot of those projects wouldn't have been possible or would have been significantly different if it wasn't for the groundwork laid down by the Python team and the Python community. I'm very keen to make sure that groundwork doesn't go away. It's taken 25 years to develop it, and it would be a shame to have to develop it all over again simply because we didn't pay attention to the way the world was changing around us. Thank you very much.
Thank you so much. Pessoal, acho que a gente não tem tempo para perguntas, a gente já pegou um pouco do horário do coffee break, mas tenho certeza que ele está disponível se alguém quiser tirar alguma pergunta pessoalmente, tá bom? Obrigada. Thank you again.